Okay, so we're going to take a look at a combustion analysis problem. These kind of represent the coup de grace of molecular and empirical formula type problems. They're a little bit tricky at first, but once you get used to them, they're not so bad. So the basic idea here is that you're going to take an organic substance, that's a compound that contains at least some carbon and hydrogen. Sometimes it contains some oxygen and other things, and you're going to burn it. And there's a little diagram you see up here in the upper right corner. So the sample's put in the furnace, and you are going to burn it with some oxygen, and as usual you get some carbon dioxide and water, and the apparatus allows you to absorb the water and weigh it, and also the carbon dioxide, and you can weigh that as well. So in this example that we did in class, you can see that the original sample had a mass of 0.225 grams, and when we're done burning that, we had 0.512 grams of carbon dioxide and 0.209 grams of water. So the trick here is to try to figure out how much of the oxygen is in the compound and how much of the oxygen was used just to combust it. So our first step is to try to figure out how much carbon is in the compound. We've got to do that by converting the 0.512 grams of carbon dioxide into moles of carbon dioxide. And then we look at the mole-to-mole ratio. For every 1 mole of carbon dioxide, we get 1 mole of carbon. And at this point, I like to stop and calculate the moles of carbon, because you're going to need that in a second. But right now I'm going to convert the moles of carbon into grams of carbon, because I want to figure out how many grams of carbon are in the compound. Next step is to do the same thing with the hydrogen. So we have 0.209 grams of water, and we're going to convert that to moles of water, and then from moles of water to moles of hydrogen. Here the ratio, you notice, is a 2-to-1 ratio. A lot of kids forget that. So that gives us about 0.0232 moles of hydrogen, and since the molar mass of hydrogen is 1, that's also the amount of grams of hydrogen. Okay, so now what have we done? We got the grams of carbon in the compound and grams of hydrogen in the compound. So if we add those together, we're going to have the total mass of the carbon and hydrogen in the compound. And we're going to use that because if you subtract that number from the total mass of the compound, then you're going to get the mass of the oxygen that was in the compound. So 0.225 grams was the mass of the sample, so that's got the carbon, hydrogen, and oxygen. Subtract the carbon and hydrogen, and what you got left is going to be the grams of oxygen. And we're going to go ahead and convert that to moles of oxygen as well. Alright, so now we're going to take a look. We're going to look at our typical mole-to-mole ratios here. We're going to divide always a larger number by the smallest number. In this case, that's the moles of oxygen. And you see that we get about a 3-to-1 ratio between the carbon and the oxygen. Do the same with the hydrogen and the oxygen. Again, dividing by the smallest number. And we get that there's about a 6-to-1 ratio between the hydrogen and the oxygen. And so that tells us that the empirical formula is C3H6O. So that's the empirical formula. Now in the problem, if you go back to it in the keynote, you'll see that they also gave us the actual molar mass of this compound, which was about 116. So from that we want to figure out what's the actual or molecular formula for the compound. Well, if you figure out the total molecular mass of the compound from the empirical formula, that would be 58. And this is exactly 1/2 of the mass that we were given. So that means that the actual compound is twice the formula, or twice the number of particles in the formula as in the empirical formula. So the actual molecular formula is C6H12O2. And there you go.